So let's get started. On May 11th, it's Monday, it's in the morning, probably 11 a.m. There's a talk by a famous professor who's the director of a school tech, a big energy center, big center between Russia and MIT. So I'm going to send the announcement, and he's been working in England for many years. Now he's coming from Russia to the US to visit MIT, so I invited him over. And I'm sure his talk would be interesting because he has a very good vision about power systems. So we talked about the stability the other day. And the stability for us was that we have a system, x dot equal to f of x. This is an autonomous system with no input. If I start from some, or x dot of t. If I start from some initial state, that x evolves in time. I start from a point in time, and x moves around. And I'm hoping that, I would hope that x settles down somewhere. Then we talk about the notion of equilibrium point. X star is equilibrium if f of x star is 0. We said whenever the right side is 0, then we are at the equilibrium, or at equilibrium. So Assume that x star is an equilibrium of a system, and I start from somewhere. I could go towards the equilibrium, I could go around it, or I could go towards infinity. So in the x space, or the space of trajectories, I might be able to go towards an equilibrium, go around, have a periodic behavior, have a chaotic behavior, or go towards infinity. And for us, stability was have an energy function that is called Lyapunov, or energy function v of x with the property that v of x is non-negative. Roughly speaking, v of x is non-negative. The derivative with respect to time is negative. An energy that reduces in time. If that's the case, under my assumptions, we go towards the equilibrium. Then we said if the system is a linear system, stability, so as long as A is non-singular, AX being 0 means X is 0, and stability is about eigenvalues, args of A. I have a real matrix, but the eigenvalues could be complex, and each complex number is a point in R2. So eigenvalues are points. If all points are in the left half plane, we have a stability. So an eigenvalue has a real part and imaginary part. The real part is important. The real part talks about attenuation of a signal or amplification, and the imaginary part talks about oscillation. So signal could go down or go up. Oscillation is about beta. Going down or up is about alpha. So if all eigenvalues are in the left half plane, we are good. If there is at least one eigenvalue in the right half plane, then the system is unstable. We also talk about control system. What if the system is not stable? And we had one more result which was important. If I have a nonlinear system, I put it here. So this is just a review of last lecture. I care about one equilibrium, x star, and I want to study the behavior around the equilibrium, this local behavior. I hope that if I start from a vicinity of x star, I go towards it. To study this behavior, all I need to do is to approximate the dynamics around that equilibrium. So instead of x dot equal to f of x, I work on x dot equal to ax, where a is the derivative or the Jacobian of f of x at the point x star. So I linearize the function, the vector field around the equilibrium, get a matrix out of it, and if args of A are in left half plane, we are done. Local stability is about first linearize the system, look at the matrix A. If eigenvalues are this side, we are good. So this is about stability. Stability in a general context of trajectories, local stability, Lyapunov for energy stability, and stability for linear system. Then we talk about what if the system is not stable. Then the problem gets much more interesting. So let's start with this problem. The first thing that, maybe we can do something else first. That would be important. Yeah.
Good question. For the energy equation, is there any, how do you make your guess? As long as it meets the constraints?
As long as you satisfy the constraint. This is still an active area of research. People who do robotics, mechanics, consider this energy function as the summation of kinetic and potential. For general system, you have to guess. So Lyapunov showed that there is an energy function, but the energy function depends on the solution. You don't know the solution, It's hard to find it. But the good news is this is not unique. There are infinitely many energy functions. So you have to guess. So now that you mentioned this, probably I should say something which is important. I didn't want to mention this, but this is related to your question. For every linear system, the system is stable if and only if there is an energy function that is quadratic. So this is one result. A linear system is stable if there is a quadratic energy function, and if there is a quadratic energy function, then this is stable. Then you would say, how can I find a quadratic function is what? X transpose px. How can I find this p? If I know the p, I know the energy. The energy function should be positive for all values. So what's the property of p? Assuming that you're searching for p, what property should you satisfy? This should be always positive. So p should be what? Positive semi-definite. Talk about the derivative. What is the derivative of this? The derivative of this is x dot px plus x transpose px dot. The derivative is derivative of this plus the derivative of that. What is x dot? Is ax. So this is ax. This is ax transpose. And if you simplify this, is x transpose a transpose p plus pax. You have a function, you want to make it always negative. So this should be negative definite. A transpose p plus pa is always negative definite. So a linear system is stable if and only if there exists a quadratic function, and for finding quadratic function, we have a quadratic energy function if and only if there is a matrix whose eigenvalues are all non-negative, for which another matrix has negative eigenvalues. So this is how we can characterize the energy function for linear system. But if you go to nonlinear system, this is still an active area of research. In general, it's hard to guess. So I got back to this story because I want to complete it before getting back to the dynamics of a generator and talking about swing equations. Another thing that we care about in practice, so there are three problems that we care about in practice. One is tracking. One is state feedback. One is output feedback. And probably talk about another one, which is decentralized control. So these are general concepts which are very useful for power. So let me spend some time on this concept, then we get back to the model of generator, we talk about swing equation, and then we go to the modeling of wind. So what is tracking? Someone has given you a dynamical system and has said, okay, this is the input that you can inject. If you inject some input, you're going to get some output. But I want to get some desirable output. Like you're driving a car, you want to drive at the speed of 60 miles per hour. The output should look like this, a constant number, call it R. How can I make a system have a constant desirable output? So that's the tracking problem. We want to make sure that the output of a system tracks a given number or a given signal. It may not be constant, it could be oscillatory, but this signal should be given. Given a system, how can I make sure that a dynamical system has an output which tracks that signal? And we want to design U. So what is the U? And we want to design so that this happens. This could be the electrical power coming out of a generator. The electrical power coming out of a generator should be constant. So this is a solution from optimal power flow. Someone solves the market problem and says this generator should generate 2 megawatts of power. So this is given. How can I make sure that the generator generates that amount of power real time? So that's a tracking problem. So the main idea is here. I replace a system by transfer function. I call it G of S. A linear system has a transfer function. Probably you've all seen transfer function. I can put it here. X dot equal to AX plus BU. Y, for example, equal to CX. So X dot equal to AX plus BU. You apply U, you get a state. And the output of a system is a subset of the state, is Cx, for example. So what is Laplace domain? If you take it to the Laplace domain, the derivative is S, capital X of S, is A, this plus B, US, Y in the, this is Y in the time domain, that's the Y in the Laplace domain. It's Cx. X sub S, and if you do simplification, Y over U is equal to what? The transfer function is input-output behavior in the Laplace domain, or you can consider it in the Fourier domain. So this is equal to what? What is the transfer function for a system like this? It's C Si minus A inverse B. You just do it in a very natural way. You have to go and review your material from signal and system. This U is in the time domain, that's U in the Laplace domain. The argument instead of T is S. And derivative in Laplace domain is multiplication by S. Then you want to calculate Y over U in the Laplace domain, that's C multiplied by a function of S is Si minus A inverse multiplied by B. That's the input-output behavior. This is transfer function. So there is a transfer function here. And we want to prove something. It's not hard, but I want to make sure you understand, to follow this part. So there is some U here. Someone gives us number R. Someone has said that this is a reference, this is the input that I want to design, and I hope that the output of a system follows this input. Then what should I do? Any idea? First, we have to make a comparison. We just subtract these two signals to see how off the output is from the reference. Then I get a signal. Then what else? So I have a system. I look at the output. I compare it with the reference. If there is a difference, I would say, okay, there's a difference. Maybe I should generate my input based on this difference. So what is the input here? Any idea? And this signal is called error. Probably some of you have taken just the classic control. This is classic control in undergrad. You should put something here. A constant gain, and a guess. This is the most fundamental thing behind the control of satellite and a lot of things in 19th century, or you can say the early 20th century, depending on what problem you're looking at. Tracking is very fundamental. There were many big tracking problems back then, like early 90s or 20s. Then you were looking at the problem as it's a very simple system. You have two numbers, you get an error. You have to form U as a function of E. This is a simple integrator. That's the notion of PID control. If some of you have heard of PID, this is the reason. If you put a simple integrator, we write the equation now, it's simple, it's guaranteed that. So this is the signal. Before time, this is signal. When time is negative, nothing is happening. For positive time, I'm getting R to the system. And the output of a system looks like this. When there is no input, nothing happens. Suddenly, I get a lot of fluctuation, and I converge to R. So this is the notion of tracking. You have a system. You measure the output, compare it to this constant number, calculate the error. Then you put an integrator. Integrator is 1 over S in the Laplace domain. Then under some mild condition that I'm going to tell you, it's guaranteed that the output looks like this. Some oscillations, then it's going to converge to a desirable signal. This part is called transient. This part is called a steady state. So when you apply something to the system, for a while you get weird signal, the system is in transient, and then you're going to have a smoother signal. That's where the system it goes towards a steady state. So to prove this, all we need to show is that the signal E of t goes towards 0 as time goes to infinity. So this is the error. The difference between the reference signal and the output. If the error goes towards 0 as time goes to infinity, that's tracking. How can I calculate the error at infinity? This is again from signals and system. The limit of a signal when t goes to infinity is what? Is the limit when s goes to 0, s multiplied by e of s. This is infinite value theorem. You have a signal. If you care about the signal at infinity in the time domain, go to the Laplace domain, multiply it by s. When s goes towards 0, you're done. And then you understand why we put 1 over s here. This 1 over s tries to make this 0. If you do the calculation, this happens. So a simple integrator. So to recap the story here, we have a system, like this is a car. You can put some gas in it. And someone has told me, put gas in any way that you want, as long as the output is 50 miles per hour. How can I do it? 50 miles per hour is my reference. This is cruise control. This is exactly cruise control. You measure the real-time speed, compare it with your reference, send it to an integrator or a PID controller, then you feed it to the system. And the claim is this error goes towards 0 as time goes towards infinity, because the error at infinity is s, which is the argument for the Laplace domain, multiplied by the signal in the Laplace domain when s goes towards 0. And if you do a calculation, you see that this 1 over s makes this 0. That's how it's going to work. And you see the calculation in the lecture note. It comes under one assumption, but the assumption is not that important. As long as there is no differentiator here to cancel out this. If s shows up here as a numerator, it cancels out s as a denominator, then this is not helpful. You have to put 2 integrators. In general, the main concept is that if you care about tracking, you have to put integrator. An integrator means take the history of a signal. If you take the history of a signal, you can do tracking. So if this is a generator, you want to get 2 megawatts output, you can put an integrator here. So that's the tracking part. So what is the state feedback? I did a state feedback here. You have a system. You apply some u, assume you get some x. X is the state of a system. And you know that this is not stable. And you want to make it stable. You put a feedback here. So a feedback tries to measure some parameters of a system in real time, then makes decision or adjusts the previous decision. And we have two types of feedback. Feedback could be a function of x, which is called a state feedback, or feedback as a function of y, which is called output feedback. So when we want to make decision for u, should we make the decision based on x or based on y? So let's focus on this problem. If x dot is ax plus bu. So you derive the system, u is the input. When you apply the input, x evolves according to the vector field ax plus bu. And assume that a is unstable. Some of the eigenvalues are in the right half plane. You want to design a feedback. The feedback could be a gain, could have some integrators for tracking, could be much more complicated. The simplest type of feedback that you can imagine is a simple gain k, just a constant number. In practice, it's not just a simple gain. They try to put some integrators, and that control is called PI control. Some of you have heard of PID. What is PID control? What does it stand for?
Proportional integral derivative.
Yeah. Proportional, which is this, constant number. Integrator, which is this. And sometimes differentiation, but differentiation in practice is dangerous. Most of the time it's just PI. Proportional constant gain and integrator to do the tracking. And let's calculate the whole thing. So this is open loop. This is feedback. The whole thing is called closed loop. So this is open loop. You apply u, you get x. This is feedback, the whole thing. You've closed the loop, it's called closed loop. The system looks like this. X dot equal to ax plus bu, and u is kx because of this. So x dot is a plus bkx. Then you're looking for a k such that this system is stable. So if you want to control a system, someone asks you to steer a system to control it, then if you care about a feedback control, like a static feedback or a constant feedback, you need to design a k such that a plus bk is a good matrix. So the question is, how can I design k such that the eigenvalues are in the left half plane? So this, probably there is one question in homework 4 or 5 about this. For example, assume that A is 1, 2, 3, 4. This is A. B, this is A. B is 1, 2, K. Looks like K1, K2. You do the multiplication. Look at the eigenvalues of A. Some of them are positive. A plus BK is a matrix which is parameterized in terms of the entries of K, like K1 and K2. And under some mild condition, there are infinitely many values for K to make it stable. Or something even better. You can design the poles of a system, eigenvalues. First, the eigenvalues of A are here. For example, 1. Eigenvalues of A, 2 of them are good, 2 of them are bad. Is it possible that I place them somewhere good? That problem is pole placement. You pick the modes of a system, the eigenvalues of a system, then design K. And that problem is also possible. So there are many ways that you can look at this problem. You can do pole placement, you can do stability, but the bottom line here is that feedback is pretty helpful. If you have an integrator, you do tracking. If you read the state and you put a K, you can always make it stable. So a state feedback is great. You can always make it stable. But the question is this practical? Can you really implement this in practice? Any question? Any idea? Can you really implement a state feedback in practice? Like classic examples are airplane. Like if you look at one of the small airplane by Boeing, the number of states is more than 12,000. And that means you need 12,000 parameters to describe the behavior of an airplane. But how many measurements can you do? Airplane is moving. You can talk about, in 3D, you can talk about like pitch angle, yaw angle, things like this. You can talk about measurement from wind. The number of measurements that you can do is not 12,000. So if you care about a system could be so complex that this X becomes very high dimensional. So this X is the state that we need to describe the behavior. We need to describe the behavior of a US grid. Maybe there are a lot of parameters. I have a generator here, I want to control it. And if I want to get the state from a US grid, God knows how many states you need. It's about a few million states. And then how can you just get this X? It's very hard. You have to collect a few million parameters in real time to make a decision for your generator. So if this is one generator. If this is the US grid and you're sitting here, there's a generator. We get to that later. You need a lot of measurements. Then this is where it's not practical. When you go to the notion of output control. So output control would tell you, no, don't worry, if you cannot measure X, there is still a way to solve the problem. So let's put it here. A system which is a linear system, X dot equal to AX plus BU. U is the input of a system. You apply it to the system. This is like the gas that you put in a car. And X could be the location, could be the speed. You do some measurements. That's the output. Y. We call it Cx. Y is a function of X. Most of the time, this X is very high dimensional. This U is small. This Y is small. And that means there are a lot of states in the system. You can apply just a few inputs to the system, and you can measure a few outputs. So you have a gigantic system. The behavior is very complex, like an airplane. You can apply some inputs, and the input for an airplane is how to control it. This is not high dimensional. And why is the measurement? You can measure something about an airplane. Again, this is low dimensional. We get to the power later, and you get a better understanding of this in the context of power. If I knew X, the problem of designing a stable causal system was easy. So assume that I have a system here. This is Y, this is U, and I want to control it. This A is not stable. So this A is not stable. You would say, okay, I put an integrator, I put a gain K, feed it back. If I put a gain K here, that needs X. I don't know X. So what can I do? If I know X, so imagine that, for example, in airplane, this is about 12K, this is about like 20, this is about 300. You have 20 inputs to an airplane. The behavior is described by 12,000 web parameters. The number of measurements is 300. If I had 12K measurements, stability was easy. But I have 300 measurements. I have 300, not 12K. Then what should I do? I put the feedback here, but this feedback needs X. Any idea? The problem was first studied by a famous professor at Stanford named Leuenberger. And that was during the war, actually. And they didn't know how to deal with this problem. He's still alive. He's at Stanford. But this is called Leuenberger observer. And after that, another famous professor named Coleman tries to optimize it. So the main idea here is, how to get X. So what you can do in practice is observer or estimator. You try to estimate X, and we call it X hat. So we try to make sure that this signal tracks the state of a system, like a tracking problem. So I don't know X. What can I do? I try to get X out of this system. I try to estimate it. So there is an observer or estimator to get X hat. How can we do this? This part is a little tricky. So you see all the equations in the lecture notes. I'm a little fast here because this is a very general concept. It's not as easy as you think. But it's good to know this at least at the high level because it helps with power. You have a nationwide power grid, and probably you want to estimate the state of a system. All you need to do is that you design something which is called observer or estimator. You give the input of a system to this, you get the output of a system to this, and once you have the input and output of a system, it tries to understand what's going on in the system, tries to estimate X. So this is the notion of observer. This is the closed loop system that you see in almost all practical systems. Leonberger tries to design one observer during like 40s probably, and after that Kalman tries to optimize this. Like Kalman filtering and Kalman control is about optimal observer in this sense. So you have a system, U, Y. If you had X, done. You design a feedback to make it stable. How can I get X? I do tracking. I hope that I can put something here so that this tracks the state of a system. I input U and output Y into the system. I put both of them into the system, and there is a simple dynamics here to give us this state. So the equations are in. So the equations are in the lecture note, but we don't care about it at this point. We want to understand how we can use it in the context of power. In the context of power, we learned that each generator by itself looks like this. So let's connect this story to power. Each generator, on one side, there are coils here, give us voltage or power, electrical power. And there is an excitation system here. So there is an excitation system on the rotating part, and also we do mechanical input. So we put some mechanical input here to do rotations. There is an excitation system here to give us current that generates electromagnetic field, and that induces some current or voltage over there. That's electrical power. That's how we go from mechanical power to electrical power. This is a standalone generator. In practice, the system that I'm talking about, like in New York, is 500 generators. So we have a gigantic system with a lot of generators, and then we want to see how we can do it. And most of the time in practice, ISOs, the model of a generator is very complicated, but for big generators, normally they approximate this by 12 states. So each generator by itself has 12 parameters to describe the behavior. So we got to this point in the last lecture. So we said the model of a generator, at least in the steady state, could look like this. Let me make sure I get the same notation. We call this EA, Jx VA. A means this is a three-phase network. A is just one of the phases, and there is some resistance in the excitation system. Is R. We put a DC voltage V or VF. This is the voltage for the field, and we get some current here. Current for the field IF. So this part is called field circuit. The other one is called armature circuit. So field circuit is this part, armature circuit is that part. And we talk about the power coming out of a generator. How can I calculate the power? If you care about power, electrical power, and you can call this IA, electrical power is the product of voltage and current. VA, IA conjugate. So I can put S, the complex power coming out of it. The complex power, S electrical. The complex power coming out of a generator is the product of voltage and the conjugate of current. And we said for a generator, there are two voltages. Voltage at the bus, which is called terminal voltage, voltage inside the generator. So you see one voltage here, one voltage over there. So voltage inside the generator, voltage at the bus. Then you would say this is VA. What is current? The current is this voltage minus that voltage over that. It's EA minus VA over JX conjugate. So the current here is this voltage minus that voltage over this. If you do the calculation, active power is norm of EA, norm of VA over X sine of theta, or put it this way, the angle difference, angle of E minus angle of VA. And Q is, so two equations, EA VA over X, cosine of the same angle, angle EAVA, minus norm of VA squared over X. So the power coming out of that is a complex power, has a real part, active power, imaginary power, reactive power. Active power is a function of a bunch of components. The magnitude here multiplied by the magnitude over there divided by the reactance, multiplied by the sine of the angle here minus the angle over there. So these are two sinusoidal functions. The magnitudes are important. The phase difference is also important. This is the magnitude. This is the phase difference. Reactive power has a cosine term minus another term. Then we said if the angle difference is positive, that means we generate. We deliver power. If this is positive, meaning that this is positive, we deliver power to the network. Power comes out of a generator. If the angle is negative, so if the angle difference is negative, that means we consume power. So here the concept is that we can put mechanical power here to do rotation, and power comes out of that, or you consume electrical power to get mechanical rotation. So a generator could generate power or could consume power and give us mechanical rotation. And that one is the type of a machine. And we said when this angle difference is equal to 0, means no active power And the name of this is called synchronous condenser. So when the angle difference is 0, we don't care about the power transfer in the active sense. We don't care about electrical power. We don't care about mechanical power. Whenever this is 0, this part is gone. It's all about reactive power. We can generate reactive power, or we can consume or absorb reactive power. That device is called synchronous condenser. So this is all a steady state. You don't see time in it. But in practice, time and dynamics becomes important. Now we can get to the control and the dynamic of a generator, which is called swing equation. So what is swing equation? So a generator looks like this. Swing equation. This is real, this is imaginary, this one is called direct. So I just write the names here, then I explain what it is. This one is quadrature. This modeling of generator is extremely important. You have a generator, a part of that, the outer part, which is a stator, is fixed, the inner part is rotating. And now the first question that might come across your mind is, how can I define a coordinate? For example, I want to think about how many rotations I've done. I want to think about angle, this angle, the angle for this, because this is rotating. How can I define a coordinate? What are the options to define a coordinate for angle? Any idea? Yeah.
Well, that's right, I think, but maybe a line to the phases.
We can talk about phases, but look at the problem from a very different perspective. There is a fixed part, there is a rotating part. Where should I put the coordinate? Should the coordinate be fixed or it be moving? There are two different components. One component is fixed. Should I stay there and look at the rotation, or should I stay on the rotating part and then look at the angle? So there are two different viewpoints for this. There's a fixed part, there's a rotating part. You can have a stationary coordinate, you can have a rotating coordinate. When we talk about power system, we know that, for example, the frequency is 50 hertz or 60 hertz. So that means we hope that the rotation is constant. So we can do two things. We can measure this angle. There are two coordinates. One coordinate that I call real and imaginary. Real imaginary is on the stator, which is fixed. There is a fixed part. I would say this is real, this is imaginary. This is a fixed coordinate. Another coordinate that I call it direct and quadrature. Direct is along this, quadrature is along that. It is rotating. So there are two different coordinates here. And then you can define an angle. The angle shows how many times they've done rotations. The angle measures this angle along this with respect to a fixed part. So this is fixed, but this part is moving around. So you have to imagine that theta increases because we're just moving around. And theta is equal to what? The way that we measure it looks like this. Let me just erase this. This part is a little tricky. You need some time to digest this. So there are two different coordinates. One is on the stator part, which is fixed. It's this part. The tilted part is on the rotor. It's just moving around. And the angle, we can look at it this way. This is the real part. This is the quadrature. We call it Q. People call it QD. So this coordinate is called DQ or QD. DQ coordinate is about the coordinate for a rotor. Call this delta. Theta is equal to delta. Delta is this part plus pi over 2 plus some frequency of rotation multiplied by time. So this equation is extremely important. What is the angle for rotation? And the angle for rotation just increases in time. You would say, I do one rotation, I do two rotations, so this theta increases in time. How can I capture that? That's the frequency for rotation multiplied by time. There is 1 pi over 2 here, and this angle is called delta. So the angle delta is the difference between this q coordinate and the real part. So this is theta. So we have 1 theta, 1 delta. One would say, why do we care about delta? It turns out that, I put it here, we had this model. I call VF, R, IF. I just erased this. Let's just keep this here. EA, X, VA. It turns out that this delta, this EA, internal voltage, is in this direction. We don't want to make it a circuit course. We don't want to talk about electromagnetic field, but this induction of voltage is in this direction. And this delta is what? Is the angle for this. So this delta is very important for us. It's extremely important because this is about the angle of internal voltage. So the mechanical rotation that you do, you have a generator, you do mechanical rotation, you see voltage over there. These are related. This mechanical rotation is about rotation, constant rotation in time, shifted by pi over 2 plus a number. This is phase difference. This phase is what? This is the phase of the voltage induced at one side of a generator. Now, what is the stability? How can you interpret the stability here? You do a lot of things. This is connected to the rest of the world. A consumer sitting here wants to get power out of a generator. And then if this angle oscillates, it's not a good thing. So stability for us is to make sure that this angle goes to an equilibrium. This voltage magnitude goes to an equilibrium. So you have a generator. You want to make sure that the complex voltage coming out of this, it doesn't fluctuate. The voltage magnitude goes to an equilibrium, the angle goes to an equilibrium. So this angle is extremely important for us. And that's about Swing equation. So Swing equation talks about this angle, which is supposed to be fixed, or this angle, which increases in time. So to give you some intuition, you have a generator like this. You need some power. I would say 2 megawatts. Power coming out of this. You put mechanical power, gets rotation, get 2 megawatts. A few minutes after that, changes to 3 megawatts. Then what would happen to this? So you have a generator, you would say, now I need 2 megawatts power. A few minutes after that is 3 megawatts. So you've got rotation for 2 megawatts. Then you want to change the rotation to 3 megawatts. It turns out that instability means you want to increase the rotation to go from 2 megawatts to 3 megawatts, but the rotation increases, go towards infinity. So that's instability. You assume the generator cannot get faster and faster. It gets so fast that it's at some point to stop, you have to stop the generator. So instability for us is that this has some abnormal behavior. If it has a constant rotation here means this is fixed, it's great, but it could happen that the angle increases, gets faster and faster, we get some acceleration, and then that simply in the trajectory space that we talk about, instead of going towards an equilibrium, we go towards infinity. So how can I make sure that a generator doesn't behave like that? So we want to talk about the dynamics of this theta. It turns out that, so most of the time we want to make it fixed. If it's fixed, it's great. If it's fixed, it means that we are rotating by a constant speed. The dynamics for that looks like this. M T double dot plus D delta dot plus P electrical is P mechanical. This is swing equation. Swing equation describes the dynamics of an angle. The second derivative of delta multiplied by m, which is inertia, plus the first derivative of delta multiplied by d, which is friction, plus the electrical power coming out of that is equal to mechanical power. Looks very simple. The swing equation was known for many, many years.
Is it S or P? The electrical.
P electrical. Yeah. So you have so putting it differently, you have a generator here. It is connected to a grid. This is grid. The rest of the world. And you put some mechanical power. P mechanical, rotation. You put some rotation into a generator, we get to wind turbines after this. This could come out of wind turbine. You put some rotation, mechanical power comes out of that, it's connected to the rest of the board. So you put electrical power, mechanical power comes out of that, or you put electrical power, rotation comes out of that. Then you would say that there is some interaction between mechanical and electrical, that's through rotation. Rotation increases over time, but there is a part which is supposed to be fixed. And that's this angle of this voltage, and that has a dynamics. Depends on the inertia, depends on the friction, depends on the difference between mechanical and electrical. So that's the equation. So let's study stability of this. If we can get something stable out of this, we would be happy. What does stability mean? What is the state of a system? What is x for this? First, we have to put it in the context of x dot equal to f of x, then talk about the stability. The stability of swing equation is really important. Like 70% of blackouts on the world. So look at this EA has magnitude part and angle part. About 70% of blackouts in the world are about this. This is not constant. Voltage supposed to be 120 or 110. It goes up or down. It's one voltage collapse or voltage instability. 30% is about this. So if it's not supposed to be this is supposed to be constant. If for any reason humans are in the loop and this doesn't converge to an equilibrium, we get a blackout. And the probability is about 30%. About 30% depends on the area. Instability comes out of this part. The rest is about voltage. So how can I deal with this? And then first let's analyze the stability. And this is related to something which is called frequency control. I have to control the frequency. I have to make sure that the frequency here is 60 hertz, it's 50 hertz, not 70, not 40. So this is the part that I control. So let me just erase this. Any questions so far? The model for, so there is one model for voltage magnitude, which is the dynamic part, one model for the angle, which is delta. The model here is easy, second order. The model for this is very complicated. This is just about mechanical. This is about electromagnetic field, it's about flux. This is very complicated. That's why most of the black hats are in this route. Again, still this is important. The probability of 30% if there's a blackout, that's just because of this. So let's put it in the context of x dot equal to f of x. So the equation is m delta double dot plus d delta dot plus p electrical is p mechanical. I want to go from this to a standard form, which is x dot equal to f of x. How can I go from that to this? You have to define a state for a system. What is a state? So what is x? What is x? It's delta, delta dot. This is a second order model, and that means we have two states. Delta, delta dot. Delta talks about the angle, delta dot talks about frequency, a residue for frequency. Then you would say, what is x dot? X dot is what? x1 dot, x2 dot is what? x1 dot, the dot of this is the second one is x2. x2 dot is the rest. x2 dot is, so x2 dot is minus d over m x1 plus p mechanical minus p electrical over m. So x dot is equal to f of x. This is f of x for us. So this is the second order model. X is delta, and the derivative of delta with respect to time. What is x dot? X dot, it should be a function of x. The derivative of x1 is x2, the derivative of x2. So this is x2, this is x1. This is x2 dot, this is x1. So this is, let's see. Probably we are missing something here. This should be x. Yeah, this should be x2. This is x2. This is x2 dot. So x2 dot is a function of x2, and you do it that way. The first thing that you need to do is, what is an equilibrium of this system? If you have a generator is rotating, you would say it settles down somewhere. That's an equilibrium. How can you calculate the equilibrium? What is an equilibrium here? Equilibrium means what? F of x should be 0. How could it happen? This should be 0. That should be 0. When this is 0, it means what? X, this part. Delta dot should be 0. This should be 0. This is 0. The whole thing is 0. P mechanical should be equal to P electrical. Equilibrium for a generator means the derivative of angle should be 0, conservation of energy. P electrical should be equal to P mechanical. If now you see conservation of energy naturally comes out of that. If there's no conservation of energy, you either accelerate or decelerate. You have to make sure that mechanical is the same as electrical. And also the derivative of that angle is 0 in a steady state. So this angle could fluctuate, but at some point it should be constant. If it's not constant with a non-zero derivative, it's problematic. So in fact, in the space of x1, x2, or in the space of x1 is delta, delta bar, equilibrium should be somewhere here because delta dot should be 0. Equilibrium should be somewhere here or over there. So we're going to calculate the equilibrium very carefully. We're going to spend some time in it. But before doing that, let's make sure we understand something. This was a generator that we talked about. EA with some angle, and we call the angle delta. Then there was some X in it. Then we said it's connected to a bus. So a generator, this is the internal voltage, which has a magnitude, has an angle, internal reactance, is connected to the bus. This is the rest of the word. You can control P mechanical. P mechanical is the rotation. You can rotate, you can spin it faster or slower. How about P electrical? How can you calculate P electrical? What is the equation for P electrical? We wrote it, just before this we erased it. P electrical depends on this, depends on the voltage here, depends on this, and depends on angle difference. So if we want to be careful here, P mechanical is a constant number, P electrical is a function of delta. The equation for P electrical, if you remember, P electrical was what? Was EA, VA, X, sine of something. If the angle here is 0, it's sine of delta. So this P mechanical is a fixed number. You do the rotation. You have no control, no direct control over P electrical. So indeed, P electrical is a function of delta, should be constant. This is a sinusoidal number, a function. This is a constant function. You do the intersection, you get delta. So how can you calculate equilibria? Equilibria means this is 0, means the derivative is 0, means the sinusoidal function is constant, and that gives you a bunch of points. So the equilibria of a generator, there are infinitely many equilibria on the x-axis. You don't need to have any acceleration, and also P electrical should be fixed. The intersection of a line and a sinusoidal function is a bunch of points. A bunch of points. So far we learned that a generator means this. Now we can get to a very interesting part. So this is the boring part because you have to understand how to model this. One would say, why do we care about it? So let's do an example to see why the model of a generator is important in practice. There is a notion of clearance or time clearance. Generator is working, everything is good in the world, a fault happens. There is a critical time. If you can detect the fault before that and clear it, the network continues working, otherwise there is a blackout. So there is a critical time. If a fault happens in the system, you have 3 minutes to detect it and bring this network back. Otherwise, there is no way to control it. There is a blackout. And that's the notion of stability. That means if I'm running the generator here at equilibrium, everything is good. Then a fault happens, I try to go towards infinity. If I detect it, I can bring it back. After a while, I get out of region of stability. So if I'm inside the region of stability for detecting the fault, I'm good, I can bring it back. If it takes too late, I get out of that, and any point out of that goes towards infinity. So it's a very time sensitive in some sense, very time sensitive control process. A fault happens, if I can detect the fault as long as the trajectory is inside a region of attraction, that's a local instability, I can clear the fault and the system recovers. As soon as this trajectory gets out of that, it goes towards infinity. There is no way to control it. So let's spend some time. So let's take a 5-minute break. Then we get to that. And I'm going to write the equation. So this is, this is a little hard. But after this, we get to the wind turbine, which is much easier than this. But wind turbine has a very similar dynamics. So let's take a 5-minute break. Then we get back to this one.
What does X, U, and Y, X out stands for?
So this input, output, U is input, X is state, Y is output.
What is the difference between input and state?
So the input
means you do something, and
like,
state means the speed or the...
No, you have a car. Input means the fuel that you're putting. A state means the location. These are not the same.
No, what about the output?
The output means the measurement, like the speed that you measure.
What?
So the input is something that you can control. Input, you can control it directly. A state is the parameter that describes the behavior. How can you describe the behavior of a car? Output is something that you can measure. So that's the difference. Measure output, U is the input that you apply, X is the parameter that describes the behavior. These are not the same.
Location is measurement or is output?
Okay, look, so here in some cases, X could be the same as Y. That's what a state feedback. X could be the same as Y. A state describes the behavior. If you can measure it, X is Y. Sometimes you cannot measure it. For example, you cannot measure road profile, something inside the car. Then Y is a subset of X.
Y is subset?
Yeah. It means that X is big, you cannot measure all of them. Like you have a generator. Can you measure the flux here, over there? That's the state. So X is the whole thing. Y is the part that you can measure, a part of that. So U is control. X describes the whole behavior. Y is whatever you can measure. If you can measure everything, it's great. If you cannot measure everything, it's a subset.
So what is X dot?
So that was the last time. X is a derivative with respect to time.
Yeah, I know, but it's
Every
the
system.
meaning of the X dot.
Okay, so that was the last lecture that we said. If you go to single equation, like this, every system can be put in data standard form. Every physical system can be put in data standard form. So this is the integral. In fact, you can type, instead of derivative, you can put integral on this side. That talks about history. X is history of f of x.
Okay, but we're using X here, but we changed Y here.
Oh, and this is the case where we can measure everything. This is the case where we can measure some of them.
Oh,
Yeah.
so the third way is much more broader than...
Yeah, this is a general case, because this y could be x, or it could be something else.
Okay.
Yeah.
And this equation, I don't understand what
Oh, this comes from Laplace theory. You have to go to signal and sixes. This is a theorem. It's called infinite value theorem. Yeah, that's infinite value theory. Yeah.
But what's the difference between tracking and feedback? Because tracking, we also adjust the output of the system, right?
No. Tracking is just for one R.
So this is only one dimension? Or?
Could be multiple dimension. You have to think about it. It's complicated. This is not just one dimensional. But this is a stability for every initial state. No matter for every x0.
X0?
Yeah. We talk about this again last lecture. This is global stability. No matter where x starts from, it goes towards equilibrium. This is about going towards equilibrium. This is about following a reference. Yeah, these are things are different. These are a little different. Yeah.
I'm just so basically we have this equation which describes the system.
Okay.
I don't really see how this relates to this. I mean, so you chose.
I chose x equal to delta dot.
Why?
So the claim is so this is a system.
Yeah.
You are free to choose x in any way that you want, as long as x dot can be described as a function of x.
Okay.
You are free to choose it.
I mean,
So this is your physical system.
Yeah.
This is an abstract system.
okay.
As long as you can put your physical system into this abstract form, you're good. You're free to choose x in any way that you want. Not every system can be put in this form.
Okay, so I mean,
you can say I define x as delta and delta plus this. There are many ways to do it.
I mean, the
It's not
reason
unique.
you chose this is so that we could have that x dot would give us these values.
Yeah, that's
Okay. So yeah.
and so putting it differently, x is the parameters that you need to describe the behavior.
Right.
How can you describe the behavior of a generator? It's about the angle, it's about acceleration,
Right.
or any combination.
But actually, it seems as though we're more concerned with what x dot would be when we're choosing x.
Yeah.
So that's what we get.
Okay, so like if you choose x as delta double dot, for example, that x dot is never f of x.
Right.
So you have to make sure that you choose x in a way that this is satisfied.
Okay.
If you satisfy this, it's not important what x you've chosen. It's not unique.
Okay. And what is this x1? I mean, so we have x2 and x2 dot. What?
Oh, x1 and x2 are so x is a vector.
Right.
I call the first integer as x1, the second integer as x2.
Oh.
Yeah, this is x1, this is x2. Yeah.
My question is just how do you do it so fast? Do you have it ready or something? Because in my head I say, all right, let's start from the right. That's my x1, that's my x2.
That's exactly how it works.
Okay.
For every general system.
Yeah.
So for ordinary differential equation, each derivative is a state.
Right. Yeah.
And then it's easy to show that you can do it this way for every system.
Okay.
Yeah.
Okay.
But in general, if it's like just one line of equation, it's easy.
Yeah.
If there are multiple lines of equation, it's tricky.
Oh yeah.
So this is just one. There are many ways to do it. There are many ways to do it.
Okay.
So it's not unique. The good point is not unique, and it doesn't affect the analysis. If it is stable, it's stable with respect to every possible formulation, because formulations are one-to-one mappings. Yeah.
Okay.
Okay. Can I ask one quick question about the project?
Sure. Yeah.
Just in general, so I mean, I'm doing my project with like solar
Okay,
power and
sure.
like efficiency, like how to improve efficiency, and I'm not sure if it's supposed to be geared towards like. Well, I mean, it's a lot of like electrical engineering, so a lot of like here's the PN junction, all that stuff.
No, probably you don't. You're electrical or
I'm
mechanical?
electrical.
Oh, you can do it that way, but you can talk about tracking, control, reactive power of PVs. We get to that in the next lecture. You don't need to design a PV. You can talk about integration of PV into the grid. How can you do max tracking? Solar it's called maximum power tracking.
Right.
Solar is just radiating, it's fluctuating a lot. How can you control it to maximize the absorption? You don't want to design the hardware part.
So
You want
what I was
to
thinking-
design that control part.
I mean, okay, so I was thinking like basic, like here's like the theory behind it. Maybe you don't go too in depth,
Right.
and then maybe discuss like it's. I mean, it's there's parameters such as like fill factor and over
Sure,
certain voltages,
sure.
and then maybe try to play around with those parameters.
Yeah, I can do.
in a
So there are a
simulation.
lot of papers. Just send me an email. I send you some of the papers on the operation part of PVs.
Right, but I'm trying to make. I mean, I want to make sure that the direction is headed in a good direction.
PV is good. As long as PV is good for this course.
Yeah, but what I'm saying is like a lot of the it's just a bunch of equations that depended on this, and I want to investigate those dependencies more. That's okay. For
I'm
this?
sure there are a lot of papers and anything that you can
But
imagine
I'm
on
saying
PV.
that's an okay way to go about doing this paper.
It's okay as long as it shows that you have put some effort in it.
Right. I mean,
And the effort could be simulation, understanding the existing equations.
okay.
Yeah.
I want to be careful that what I'm doing relates to this course enough.
Yeah.
Because a lot of the things in this course are just giving you a foundation of the power systems, but there are not many tools that we. I mean, I'm not sure I'll be using enough of the tools we've gained through this course when doing my paper. But that's okay to do to go into something on my own that's power.
Yeah, that's
systems.
fine. Yeah, the thing is that I didn't talk about that part. I mentioned in next lecture. This is simulator.
Right.
You don't need to learn it.
Okay.
Yeah,
just have
that's
a
why
quick
I want to make sure. Yeah, go
Are you going to
ahead.
start the lecture as soon as you finish talking to him, or do I still have a couple of minutes to go get a coffee?
I'm gonna start in 2 minutes. Yeah, 2 minutes. Yeah, the thing is that you don't need to understand, like I talk about that modeling of generator. I'm going to talk about solar panels give you similar equations.
Okay.
But you don't need to know it. Because if you give it to a simulator, it does it for you automatically. And if your paper is that, it's not a good paper because you haven't put any effort.
Right.
MATLAB simulates everything for you.
Right,
so you have to make sure that there is some effort.
I
And
was
that
going
effort,
to, so first of all, like it's a lot of like reading papers to understand solar cells, and then I was hoping to make like a simulation that like I wrote myself for MATLAB. To
Yeah, if you write it yourself and you put the code in the paper, that's different. Yeah.
Like you know, basically we can adjust these parameters, which make sense in these manners,
Yeah.
and then we can see what compare.
Yeah, you can try different scenarios and say how, under different operating point, how does the solar panel
Okay,
work.
yeah, exactly.
Yeah, that's fine.
That's good.
That's good. Thank you. So let's resume the lecture. So if you have a synchronous generator, two parameters are eventually important: angle and voltage magnitude. So two parameters are important: angle and voltage magnitude. The parameters that you're allowed to control are PM and VF. Let's make sure I got something. So before doing this, let me just remind you about some facts. We had excitation system, which was VF, IF, E, A, angle delta, X, VA. We can assume that angle is 0. Then we can learn that mechanical power controls electrical power. VF controls voltage magnitude. So if you play with the excitation system, the DC voltage, that affects voltage magnitude. If you increase or decrease rotation, that affects electrical power. And both PM and VF affects frequency. They affect delta and delta dot. That's swing equation. So P mechanic generator was like this. Again, we need this picture. Power comes out of that, P electrical. There is some voltage magnitude. P mechanical goes into this. And there is an excitation system, voltage. This voltage that you apply on the rotor affects the voltage magnitude at the terminal. Mechanical power affects electrical power. Their combinations through swing equation affects frequency. So now we have two types of control. One is called voltage control. One is called frequency control. So what is voltage control? So in voltage control, you would say, I have a voltage reference. Again, it's like tracking. The voltage in my house should be 110 volts. If it's not 110 volts, what should I do? This voltage is related to that voltage, is related to excitation voltage. So I want to do tracking. If the voltage here, the voltage coming out of a generator, is not what I care about, I have a reference, I make a comparison. I compare these two numbers, and you can put an integrator here or do something about it. The important part is this part. PSS. Voltage control, because about 70% of blackouts or power outages related to voltage is a complicated process. We have to make sure that this voltage has a desirable value. Someone had designed this value for us. This comes out of optimal power flow. Like, remember this picture? Generation, transmission, distribution, and when we solve optimal power flow, we calculate voltages here. Optimal voltages. These optimal voltages are references. How can I make sure that in real time I follow it? I track it. I measure the real-time voltage coming out of a generator. So the thing is that if everything is perfect, I design the network in a way that this is optimal. But humans here fluctuate. People play with switches, and that means fluctuations. I'm not going to get the volt. I designed this for the ideal scenario. In real time, this is not the value that I care about. So I get the difference. Then I would say this angle also helps a lot. I send the angle through a feedback. I get their combination and feed it back here. So we know that this voltage, the output voltage is affected by the internal voltage is affected by the excitation voltage. So I design a feedback. The excitation voltage depends on the measurement, depends on the reference, depends on a feedback of the angle. And this part is a challenging part. We're not going to talk about it because this could be another course. PSS stands for Power System Stabilizer. It helps to stabilize the system. This is like a feedback control to make sure that all eigenvalues are in the left half plane. We want to make sure that the system is stable. So I'm not going to talk about these blocks, but I just want to give you a big idea. You have a generator. If you don't get the desirable voltage, you control the internal voltage. How can I control this? This is here, VF. V excitation or V field is a function of the output of a generator, reference, and a function of the output frequency or angle, which goes through a feedback, which is PSS or power system stabilizer. And this is about like 1 or 2 chapters of the book. This is very complicated, but the main idea is to design it. This is an integrator for tracking, but to design it in a way that eigenvalues are in the left half plane. But this is voltage control. Frequency control is nicer. So voltage control talks about this part. This affects that. Voltage affects voltage. Frequency control is about this. Mechanical power talks about frequency. If I put more power, I get a higher electrical frequency. If I put less power, I get lower frequency. So this signal comes out of that, has a frequency for going up and down. This is mechanical frequency. Rotation means electrical frequency. These things are related. Mechanical frequency, which is about rotation or spinning, is related to oscillations on the electrical side, which is mechanical frequency. So we can control it. If I measure this, this is not 50 or 60 hertz, I have to control it. I have to control this based on the measurement that I get. Again, it's a similar picture, but let's make it concrete. Yeah, go ahead.
This is the voltage control for one generator, but what about the grid when you have like multiple generators on the same grid? How do you design like a overall control of that, or?
So we get to, I briefly mentioned that that's what the decentralized control that I wrote here, I didn't mention it. That's one of the challenges. All generators come with their own controllers. The design of their controllers are not coordinated. In general, there is no guarantee on stability. So that's one of the main challenges for power grid. That for one generator, I designed this. For another generator, I designed it. But no one knows what happens if I connect them. If I connect multiple generators to a system, there's a control center which has a bunch of control parameters to compensate for their counter effects, but in general, there is no guarantee. That's why we have blackouts. So that is still an active area of research. How can I design them simultaneously? One generator here, one generator over there, design them simultaneously. I mentioned some facts about this, but the notion that people use in power is called infinite bus. So what is infinite bus? So what is infinite bus? I bought one generator, I connect it to the grid. The notion of infinite bus is that I'm so tiny that no matter what I do, it's not going to affect the behavior of a network. So I design my own controller independent of the rest of the world. I assume that this voltage, this frequency is always fixed. And can you give me an example where this is clearly violated? The notion of infinite bus doesn't make any sense. Any idea?
It doesn't make sense.
Doesn't make any sense.
I don't know, like island that we have like the main generator that's like Apple.
Yeah, if they're talking about an island with 5 generators, you cannot say that there's just 5 of those. You cannot say that if I remove it or put it, it's not going to affect the behavior. That 1/5 of the behavior. And that's the notion of microgrid. If the grid is tiny, it's not like a country, the design is really hard. That's why microgrid is one of the active areas of research. They don't know how to deal with this fact. So in fact, in practice, they assume that the rest of the world has a lot of inertia for rotation, that your rotation cannot affect their rotation. But if you're a big player, being connected or not connected to a grid affects the rotation of the rest. So that's one of the challenges. As long as the notion of infinite boss is satisfied with grid, we are good. And actually, this is the main reason why, one of the main reasons why wind is not that popular. The modeling for wind is the next lecture. If you have a lot of wind turbines, you don't know how to control it, because wind turbines just exhibit some random behaviors, and you have to have a coordinated way of designing this. And what people try to do is that instead of one wind turbine, they have a wind farm. They don't try to put it in your house. They have a lot of wind turbines, in an ocean, on top of a hill, to make sure that there is an aggregation and one controller, one control unit for the whole thing. Otherwise, if I design them separately, I don't know how to deal with this. So far we learned that voltage at the excitation system affects the terminal voltage. Mechanical input affects frequency. So here we have a feedback. So what is the feedback here? Let's talk about the feedback for P mechanical. For P mechanical, I have a reference, P reference. Again, I measure it. I compare these two numbers. I put an integrator. I put a gain and send it here. And this part is really nice. I measure the angular frequency. Most of the time, I get the derivative to talk about the frequency. Compare the frequency with P mechanical, and then you can remove this because of that integrator, put a gain. So let's spend some time on this part. The intuition is simple. You get a lot of oscillations, and this oscillation is time, frequency electrical. And there is frequency mechanical. Electrical frequency is supposed to be 60 hertz. It's not 60 hertz, it's going up and down. So frequency is supposed to be 60 hertz, it's not. That means this signal, it tries to squeeze here, tries to stretch in another period. And there is a frequency for rotation. Then how can I design this? How can I design P mechanical as a feedback? And there is a reference, like call it 60 hertz. Then what is this block here? Assume that I like to get 60 hertz, but I get 50 hertz here. Then what should I do? Then I increase the rotation. This is a positive gain. If I see that this is 50, I was supposed to get 60, it means that I have to make it faster. If this is 70, I make it slower. It's a simple gain. This is frequency control. It's very effective since 60s, and the main idea is the following. You have a generator here. I connect it to the rest of the world. I don't know what other people are doing. When I connect it to the wall, I measure the frequency over there. That frequency is an aggregated signal for the rest of the world. If that frequency is less than 50 hertz, I'm slow. If it's more than 50 hertz, I'm too fast. So that's the notion of frequency control. Again, you would say, this is a heuristic. Maybe this is wrong. Because if everyone takes actions based on this, maybe they have some counter effects on each other, we don't get stability. That's another challenge. So real world for power system is just based on heuristics, but good heuristics. It comes with a lot of power intuitions. And at least it's working now, but no one knows what happens in 20 years. Because when the dynamic changes, instead of big generators with a lot of inertia, we have people wind turbines, solar panel, microgrid. These heuristics may not be effective. So we control internal voltage based on the external voltage. We control mechanical power based on the output frequency. So that's the main idea of control. Now, a related problem is the following. I write this carefully here. Assume that a sequence of events happens. First, the system is operating well at a steady state. Everything is good. I'm just operating the system. I get the voltage of 110 volts, frequency of 50 hertz. Good. Then, suddenly, a big load joins the network. Con Ed, power operators, ISOs have no idea what you're doing in your house. You suddenly turn on your washing machine. A load joins the network. Then, what would happen? The first thing that happens is what? Not directly voltage. So load is about electrical power, and electrical power is about frequency for rotation. Then suddenly frequency drops. So if a load joins the network, I'm operating the network at the frequency of 50 hertz. If a load joins the network, the system directs, the frequency goes to like 45. Of course, it goes down by epsilon. Assume it goes from 50 to 45. Then what would happen? Feedback control stabilizes the system around a wrong frequency. The first thing is that when the frequency changes, you have to make sure that it's like a trajectory. You were here as an equilibrium, suddenly you jumped over there. Then you have to make sure that the trajectory from here doesn't go towards infinity. Feedback control stabilizes the system around the wrong equilibrium, goes to another equilibrium. So what would happen? You have a system is operating, it's an equilibrium. This is the point that you're happy. A big load joins the network, frequency drops, you go to another point. Then you have a feedback here. What is the role of this feedback? They would say the trajectory all converges slowly to another equilibrium at a lower frequency. But it doesn't go towards infinity, we are happy. But the frequency is low. Yeah.
Professor, imagine like you got like an isolated, I don't know, system. For instance, I got a generator and for a house.
Okay.
Like 1 kilowatt generator per house.
Okay.
When I turn on the washing machine, like the voltage goes down.
Okay.
But you say that the frequency drops.
The frequency drops.
But you can see the voltage because also.
Yeah, okay, that's another thing. So I was trying to say that there are two different mechanisms here. One is this mechanism, one is that mechanism. These things are independent. We are focusing on this. This is much more important. Because at the end of the day, you're talking about actual work. And work is mechanical power. Of course, you have to make sure that there is no voltage collapse. But voltage collapse is easy. If something goes wrong, this power system stabilizer takes care of the voltage and makes sure that it is stable. You can bring the frequency back if you have enough reactive power. Sorry, you can bring the voltage magnitude back to the original number if you have enough reactive power. So here I'm saying that a big load joins the network. If the load is active power, most of the time it's active power affects mechanical power, not this. So if active power joins the network, it's about mechanical power, it's about active power, as we are saying. It's not about, and active power is about frequency. So what you're saying is that a load could affect voltage magnitudes. Theoretically, yes, if that affects reactive power. And power system stabilizer is really good at this. So, but we have to make sure that both routes are good. The first route is very challenging. If a big load joins the network, the system would say, I have a system, before equilibrium, P electrical, P mechanical. P electrical should be the same as P mechanical. Suddenly I try to get a little P electrical because a big load joins the network. Then what would happen is that this gets a slower and a slower rotation. That's the stability. The frequency just drops. So when something joins the network, I'm not at equilibrium, I move. But do I go towards infinity? The whole role of these feedbacks is to make sure that no, we don't go towards infinity. We go towards a wrong frequency. Then what should I do? What is the next event that would happen? I'm stable, but the system is not 50 hertz, it's 45 hertz. How can I bring it back to the original equilibrium? You have to do what? Then we have to design the only way at equilibrium P mechanical should be the same as P electrical. When we have more P electrical for any reason, the only way that I can compensate for that is to increase P mechanical. So then I have to adjust P mechanical. So whenever a big load joins the network, we cannot make a decision right away. The system automatically behaves like this. Frequency drop, drop, drop. You go to wrong frequency. Then an operator would say, okay, I'm realizing that something is wrong. Adjust P mechanical. This part is called primary control. This part is called secondary control. So we have two steps. Primary, then secondary. Primary control, secondary control. Primary control would say, if you need more power here, you can get it, but frequency drops because of this feedback. So these feedbacks in real time are primary control. Secondary control would say, at the end of the day, if you need more electrical power, you need to burn more fuel, you need more mechanical power, you have to adjust it. How can I adjust it? That's P reference, that's optimal power flow. So optimal power flow, if a big load joins the network, you have to change the reference. That's secondary control. And people call it AGC, automatic generation control. So automatic generation control talks about the reference, that's secondary control, real-time feedback is primary control. So let me just put it here. You have a system. This is a generator. There is a feedback, and there is a reference. If consumers or humans change their behaviors, feedback takes you to a stable equilibrium, but it's a wrong equilibrium. This is primary control. You're at the wrong equilibrium for 2 minutes. Nothing happens. Then you solve an optimization to design the reference, that's optimal power flow, and that secondary control that is called automatic generation control, because there is an automated way of solving this problem. So primary control, secondary control. Now let's get to something which is, this is the last part in the swing equation. Generator, grid. This is a healthy system. A healthy system described by M double dot D dot plus P electrical with sinusoidal, like sine of delta P mechanical. A fault in the system means the following. A fault in the system means this is disconnected. For many reasons, you would have a fault in the system. Lightning happens, a line is out. Tree falls down on a line, or there's a mechanical failure in the system. How does swing equation change if a fault happens? So this is the behavior of a generator when you're connected to the grid. What if you're not connected? Then how should you adjust the dynamics? What would happen if there's a fault? What is the new dynamics? Yeah.
If there's a mechanical failure, that would be 0.
Oh, there is no mechanical failure. This line is out. Fault means the line is out in this case. How can you adjust this? What does it mean in terms of dynamics?
Means there's no rotation.
No, the rotation is you're applying mechanical power here, but you don't deliver power to the network. The electrical is 0. Fault means electrical is 0. It's open loop. So when there is a fault, something is disconnected, effectively what you're doing is that you can say the fault is mechanical fault. Effectively what you're doing is that you don't deliver the power that you were supposed to deliver. Remove it. Then the story for fault is very interesting. We said that in the space for delta, delta bar, there are equilibriums. Equilibrium here, 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 for example. We calculate equilibria. Then it's easy to show that this is a stable. And if you're inside this region of attraction, you go towards an equilibrium. Whenever you're out of this, you always go towards infinity. So all other equilibria are not stable. So for a power system, there is a good equilibrium with a small angle. If the angle is a small, is a stable. If angle, this is angle, that's a derivative. If angle is big, positive or negative, it's not stable. Then, if there is some fluctuation, you're operating here, then there's a fluctuation. That means you jump from here to over there. If the jump is not a lot, you recover, get back there. So this is about this part. Whenever there is a fault, so let's do the diagram. We are here. We are at the good equilibrium. The system is healthy. Then suddenly, we start from here with a new dynamics. So I start from a right equilibrium for a healthy system. A fault happens. I'm here, but the dynamics has changed. Can just solve this equation. It's easy to show that if you solve that, the trajectory looks like this. Goes towards infinity. So whenever a fault happens, if this is gone, if you solve a second order equation, delta and delta dot both increase. Then what would happen? The story gets nice here. After t seconds, the operator cleared the fault. So after 2 seconds, 3 seconds, 2 minutes, you realize that there's a fault, you diagnose it, you clear the fault. The claim is when t is small, the system recovers. When t is big, which is the critical time, you're going to have blackout. And the idea is, so let's get your idea in this. Does this make any sense? You have a system, If you're at this equilibrium, you're good. If you perturb it a little bit, you come back there for this dynamics. Suddenly you change the dynamics. For the new dynamics, if you're here, you go towards infinity. Then at time t, you get back, you clear the fault. Instead of here, you're over there. At time t, you're over there. You switch to the right dynamics because you clear the fault, it's coming back there. Then what is the right t or what is the wrong t? Whenever a fault happens, we try to go towards infinity. Operator would say after 2 seconds, I realize that, okay, there's a fault, stop. We stop here. Then we reconnect the line. Now the dynamics here. So this, I'm here. There's t. If I'm inside this region, I can come back over there. If I'm outside the region, I go towards infinity. So that's the main idea. If a fault happens, the dynamic changes. The system behaves crazy. When we clear the fault, we stop there, look at the original dynamics. Is this point too far away from the equilibrium or is it close? So this time, which is called critical time of the boundary, is really important. That's why clearing the fault is important. If a fault happens in a network, you have like 5 minutes, 6 minutes to clear it. If you do it after 20 minutes, it's too late. It's propagated. You see instability. So this is the notion of critical time. Now let's go to renewable energy. So when we talk about generator, we talk about mechanical power. Where does mechanical power come from? You would say, I need rotation. I can get steam to do the rotation. I can use water, it's hydro, or I can do wind. So wind power. So what is wind power? The idea behind wind power is the following. Wind is blowing from one direction. There is a turbine. Wind speed is not enough for 60 hertz. You have to put a gearbox here to increase the booster rotation. Then this is the mechanical rotation for a generator. You connect it to the shaft, and this is electrical. P elect, P mechanical. So a wind turbine tries to convert wind power to mechanical power. So when you talk about wind, don't assume that you don't need a generator. Every wind turbine has a generator. It's attached to a generator. You eventually need to convert mechanical to electrical, and the whole role of wind turbine is to convert wind power to rotation to get P mechanical. So when you talk about like wind generation, wind tower is the whole thing. So wind tower that you see like on mountains, in ocean, offshore, it's the whole thing. There's a tower, you see blades, and most of the time this is mounted on top of that. There is a generator on site. But you can imagine that theoretically there is some energy in wind. And there is some mechanical power coming out of this. The first question is, how much power can you capture? There is some energy in wind. There is some energy in radiation. Can you capture it all? Any idea? You're the best designer. You talk about mechanics, aerodynamics. You design the best turbine in the world. How much power can you capture? Can you capture the 100% power in the wind? What is the limit? Is what? Okay, what's the number? 59. The maximum power that you can capture is 59. So let's write the formula. This is important because we have to do control over it. When you know that you cannot get 100% of power, it's 59%, and 59% at best. How can I make sure that in real time I'm getting the best power out of it? So let's write the equations. So you might have heard of pitch control for generator, different types of control. It's really about capturing the best amount of power that you need. So there are a bunch of parameters. Air density, rotor swept area, beta, blade, pitch, angle, lambda, tip, speed ratio, which is defined as omega r over v. So wind speed is denoted, or the velocity is denoted as v. The angular rotation is denoted as omega. The radius is denoted as r. So we have a bunch of parameters. You have some blades here. When you do rotation, you cover an area. It's called A, rotor swept area. There is an air density. There is some angle for the blades. You have a tower, there is some angle for the blade. That pitch, or if you try to move the tower, is yaw. We don't talk about yaw, we just talk about pitch angle. And lambda is very important. It's called tip speed ratio. The ratio here is important. You see some speed over there. This is the angular velocity multiplied by the radius is the speed divided by wind. So you might assume that if you have, and we get to that in a second, you might assume that when you design a wind turbine, you put it out there, the speed here is the same as wind. It's not the case. The speed is different. Yeah.
How does wind have a velocity? I thought it was like measured in knots.
So here, look at it as that everything goes in the horizontal direction. This is the speed. If there is a direction, like a velocity is different from this, you have to adjust this. Assume that there is vertical blades and there is a horizontal wind with the speed, and that's it. We haven't got to the equation, but what is the equation? P aerodynamics is 1/2 Cp lambda and beta rho a v cube. And this one is called power coefficient. So P aerodynamics is the power that you can capture here. The power that you can capture, P aerodynamics, is 1/2 a factor which depends on the tip ratio and the pitch angle, multiplied by rho, like air density, the area for the covered by the blades, and the speed cube. And we talk about this later. So this is the power that you capture, the power which is available. There is one power here, one power which is captured. The power which is available doesn't have this part. It's 1/2 rho a v cube. So if you look at this, you talk about efficiency, you capture power by this rate, which is always less than 59%. So this is the maximum power that you can capture. This is the power which is available. The difference is the coefficient, power factor, which is at both 0.59. And that means, roughly speaking, you can capture half of the power in wind, half of wind power. But let's talk about this. How does it look like? This is a function of, if you have two blades, a speed at the tip, and also the direction for the blades. It looks like this. Like lambda, this is Cp. Lambda could be 5, 10, 15, things like this. For different betas, looks like this. like beta equal to 0, beta equal to 10, for example. This is a three-dimensional curve. Cp depends on lambda and beta. Fix beta and draw it as a function of lambda. When you fix beta, beta could be 0, 0 angle straight, 10 degrees. Then you would say it's not the case that when lambda increases, the efficiency increases. It's a curve like this. There is an optimal value. We have to capture this point or that point. So this rotation should not be at the minimum or at the maximum. We have to make sure that in the real time we get the right value. So if you care about capturing the best amount of power in wind, you have to make sure that in real time you get the right value for this, and you care about all these peaks. So to write it here, how can I maximize efficiency? There are two ways to maximize efficiency. That means I need to maximize Cp, lambda, and beta. So how can I maximize efficiency? Any idea? How can I maximize this? There are two feedbacks that you can put. So we have to control something in real time. Control is the feedback. You measure something, make decision, put it back. How can I do this? I can either control beta or lambda. Controlling beta is called pitch control. Controlling lambda is what? Controlling lambda, lambda is what? Omega r over v. V is wind. You cannot control it. It's just torque. It's just that omega is torque control. Torque control. So two ways to maximize efficiency. Control beta or lambda. Beta, you just play with the blades in real time. A lambda is what? I cannot control wind. It's out of control. It's not dispatchable. I cannot control the design. I can control this in real time, and that's the rotation. Maybe there is a feedback here that I can control it. And there is another thing which is important. Wind speed, we measure it as meter per second. There are three important numbers: 5, 3, 15, 25. Wind could be a little, reasonable, too much, gust, turbulence, and continue. So there is a wind speed, which could be any number, and then you need to make a decision. Whenever wind is blowing very slowly, what is the right decision for capturing power? Wind is very light. Then what you should do? What can you do? So wind is very slow, then it tries to do rotations, but that's not stable. It's not steady. You just shut it off. You don't use it. If the wind speed is below a threshold, you never use it. It's useless. If you try to capture this rotation is so slow, that's more like a disturbance. And that disturbance is more unstable than stable. You just ignore it. How about this, 25, after 25? What would happen? Wind is a lot. Again, what's the optimal decision? Turn it off. You never want to use it when there's a superstorm. It doesn't make any sense. So again, turn it off. Here, there is a period where it's a reasonable period. Wind is in a good range. You try to maximize efficiency. And what was the equation? 1/2 rho A V cubed Cp lambda beta. If you maximize efficiency, as wind increases, power increases. But what is the curve? It's cubic. Power goes up like this. So when wind is a little, it just blows, it's very light, you don't use it, ignore it. From 3 to 5, you would say that's great, that's a reasonable range. The turbine is designed to operate. In that case, we don't hurt the system, we don't damage it. So try to maximize capturing energy. According to this equation, it's cubic, goes up. And then when wind gets a little bigger, you would say, if I want to capture more than this and go up, I'm going to damage it. I don't try to maximize capturing. I try to make it constant. So there are a lot of power here, but I don't want to damage the infrastructure. I don't capture it all. Again, I control it, I keep it constant. After that, you would say too dangerous, just turn it off. So there is a curve like this. It's off, off, maximize efficiency, constant output. There is a difference between conventional generator and a generator like this. Like if instead of wind, you just burn some gas, get steam, and from steam you do this, then you can control the rotation. You would say, if I double burning fuel, probably I'm just doubling the electrical power that I'm getting there. Here is cubic. And what does it mean exactly? If a power operator miscalculates the wind speed by delta, the electrical power which is delivered is miscalculated by delta Q. So that's one of the main challenges for using wind power. This is cubic. A miscalculation in wind, especially when we are talking about real words about forecast for wind for the next half an hour. If that's wrong by epsilon, the output that you expect to get is wrong by epsilon squared. And that could be a huge positive or negative number. So this is one of the challenges. And to deal with this, there are two strategies. There are two types of generators that people care about. So first I write it, then I explain what it is. So there are two types of wind turbines. Fixed speed, variable speed. So before talking about the pros and cons of fixed and variable, let's try to make a guess. You have an infinite bus. Infinite bus means a wall, there is an outlet, it's connected to the rest of the world. You have a generator, you put it in the backyard, wind is blowing, you just connect the generator directly to the grid. Then what is the speed that you get here? What is the speed of rotation? Is constant. So wind is blowing here, is fluctuating. You have a generator connected to the rest of the world. Then what is the rotation that you get here? Is it constant or fluctuating? So wind is fluctuating. The generator, a turbine here, and it's connected to the rest of the world. So there is a generator here, there is an infinite bus. So we say wind give us rotation, rotation goes to gearbox, it's electrical power, then electrical, mechanical, mechanical, electrical, rest of the world. Then what would happen? This is fluctuating. So this is fluctuating. Wind is going up and down. Frequency here is 50 hertz. Then what would happen? It's like a paradox. On one side, electrical frequency is fixed. On the other side, the wind is just fluctuating. Then how would this intermediate device operate? What would happen? Fluctuate or is constant? It's constant. Of course, it's hard to do the experiment, but the whole point is this this frequency electrical gives you frequency mechanical. This torque that you get here comes from the rest of the world. No matter what happens here, the rotation is taken away from the rest of the world. Because this rotation talks about rotation here, frequency mechanical. This has a lot of inertia. No matter what you do, you cannot change the frequency of the grid. This is frequency electrical, comes from the rest of the world, and this frequency electrical fixes frequency mechanical. So this is one of the disadvantages. If you connected wind turbine to the grid, you would say, of course, when wind is fluctuating, I expect to get fluctuation. That never happens. Then what does it mean exactly? Then that simply means it's too much stress on the device. So no matter what would happen, this try to withstand the fluctuation over there because of this. On one side, it's supposed to be fixed, on the other side, it's not. This goes by the infinite inertia that gets from the other side, and it withstands like the fluctuation here, just as a stress. You're going to damage the device very quickly. So it's a stress, but it's simple. A simple design and low efficiency. I put it here. So a simple design and low efficiency and power fluctuation. Why is that the case? Remember the equation for power here. It's 1/2 rho A V cube, what? There was something else. Cp of lambda and beta. What is lambda? Omega R over V. If this omega is always fixed and V is fluctuating, power is fluctuating. So the power that is delivered to the grid is fluctuates. The speed is fixed. But the power that you get fluctuates in real time. So this omega is mechanical rotation, which is connected to infinite boss, is electrical frequency. There's one-to-one correspondence. This is fixed. When this fluctuates, this is not maximum efficiency. Power fluctuates. So you will say, I want to deliver power to a consumer. The consumer says, I need 2 megawatts of power, 2 kilowatts of power. This fluctuates. This is useless. I cannot use it. Then I go to something which is called variable speed. Fixed speed means just, in a very naive way, connect the turbine to the grid. It's the most natural thing, but it's not efficient. Variable speed is reduced stress and high efficiency. But the question is, how can I do this? I want to make sure that when wind changes, this changes. When V changes, omega changes, so I can maximize this. So how can I change omega in terms of V? So omega is rotation here, V is the wind that I have no control over it. Any idea? So what the main challenge here was that since we are connected to the rest of the world, this electrical frequency gives us mechanical frequency and no one can change it. Wind is not allowed to change it. Maybe I need a decoupling here. If I do some sort of decoupling here, I can get variable speed. So the main idea is this. Again, gearbox, generator. I don't want to get the frequency from the grid. How can I get rid of frequency? I should put something here. How can I get rid of frequency? As long as I'm connected to the rest of the grid through electrical frequency, I get constant mechanical frequency. How can I decouple them? Yes? We can put a battery, but it's a special case of this. In general, what's the bigger concept? Yeah, there's a coupling AC to DC. This is an AC signal, fluctuate, make it DC, make it constant. And your point is put a battery. The battery comes after this. Once you make it DC, then you make it AC. So there are two converters. This is an AC signal, fluctuate, make it DC fix, and then there is another controller, make it AC at any frequency that you want. So you can do decoupling. You would say, I put two converters. Now, since this doesn't exist, decoupled between electrical frequency and mechanical frequency, the rotation really comes out of wind turbine. There is a direct correlation, but there is a challenge. Can I send a lot of power through power electronic devices? If you do circuit, you would say this is a huge device, it comes with a loss, and this is like a processor. Can you process a lot of power? The answer is most of the time no. Theoretically, this is possible, but it's very hard to design. If you design this, it comes with a lot of inefficient, like a lot of loss, and you damage the device very quickly. Then there is, so this is one concept is fixed, just connected to the grid. Another concept is 100 decoupling. The one that you see in the board is none of them. It's variable speed, but it's designed in a more intelligent way. I'm going to just mention the name in the next lecture if you spend time on it. And after this, we go to solar energy. So this is really important. You have to really understand this to understand what wind means. Because wind means fluctuation. You connect it to the grid. Someone asked in the last lecture that how can I get excitation system? Excitation system needs power. So when we talk about excitation system, this is a stator. There is a rotor part. There is a rotor part inside, and there is an excitation system here. Maybe I can get a feedback from the grid and put control here. So what you do is that you connect the generator to the grid directly. You get a feedback from the grid, control excitation system. And it turns out that here, by this control, you can control the frequency. Here you get variable frequency. By controlling this part, you can make the frequency 50 or 60 hertz. What is this control? It's like pulse burst modulation, we get to that, but these power converters are there. So that's how we do it. And this is called doubly fed induction generator, or DFIG. Almost all wind turbines in the world, at least the previous generation, was DFIG. You have a turbine connected to the grid. You like to get 60 hertz here. You just fluctuate here. It goes from 70 hertz to 50 hertz. You have no control over wind. What can I do? If I connect it to the grid directly, then I get 60 hertz here, but there's a lot of stress, and I didn't maximize efficiency. I connect it, get a feedback back, and there is a way to make sure that this frequency is 60 hertz, and this speed is variable, and this CP is maximized. So in the next lecture, we take it from there, then we go to the modeling of solar energy. Okay, I stop here.
So many questions.
Sure.
So this is like the control system associated with this, correct?
With the generators,
With
yes.
the generator. So first of all, these are the inputs. You're saying
These are the inputs, yes. This is the mechanical power
yeah.
that you can control it. This is the excitation system.
This is like a mechanical generator. It's like this kind of thing.
Yeah, this is that.
Yeah.
Yeah. The rotation here is this.
Right.
The winding over there is connected to a battery, and this is VF, excitation system. These are controllable.
So then these are the outputs.
These are the output. Then there
the
are two
output
lines
control.
coming out of it, and that's voltage. The voltage is magnitude and phase.
Okay, and this phase.
Again, you read it. You read it, you feed
What
it
is
back.
this?
So we want to compare phase with power.
Right.
Phase with power are not correlated.
Right.
Power is correlated to frequency. So first we take the derivative to make frequency out of it.
Okay, I see.
Yeah. So we just make the units the same. They don't have the same nature.
All right. So is this is minus and this is plus?
Or yeah, we just make a comparison. Do something. Yeah.
Okay. Also, for undergraduates, you finish the project.
Oh, your undergrad? The deadline is the last day for submitting grades. Just check it with the registrar's office. But the grading system is different. Like people who have 1 month extra, they have to deliver a better
If I want
project.
to work more,
Probably it's
I was
about,
thinking to like do a lot of work like this week on the project.
Yeah.
Except that now we're not going into solar till which lecture?
okay. The solar is next lecture.
Okay. That's
Yeah,
okay.
next lecture. Probably it's about June 1st. Just check with the registrar's office.
Okay.
Yeah, no, sorry. It's
No.
about May 17th.
May 15th.
No, so for us it's like 17th.
Okay.
Yeah, you have a lot of time. Still you have time. Yeah.
Okay. So would you say hold off maybe work till next lecture or?
Yeah, you can do it that way. Yeah, we get to the solar and then you make a decision what you want. Yeah.
So for my project, I was thinking something related to the work that I do, which is
Okay.
like solar power desalination.
Okay.
But usually when we do models of like PV and everything, we come up with the power that PV would generate according to the resource using all the solar.
Oh, that's fine. As long as it's about power,
Right.
in the context of operation, it's good.
But my question is, because we usually model that and then we get the supply and the demand, and it's just like accounting. It's like supply minus demand and see
Okay,
if
so you
need
don't
it.
you don't consider physics.
Well, we not of the grid.
Yeah.
It's just like, oh, we assume losses or we
Sure.
don't or whatever.
Sure.
So my question is, in the real world, what
So there are a lot of
power flow like the
there are a lot of papers on this that if you want to do actual practice, real time,
Yeah.
you must write laws of physics explicitly.
Well,
But if you talk about planning, like I talk about market, prices, how much power I need, you can ignore laws of physics to come up with an approximate strategy.
Right.
So you can say supply is demand plus 2% loss. It's not wrong
but
because
the actual implementation of the grid and all that stuff
yeah,
would require
you
this.
require this. Yeah. So these are different things. You want to make a
more about
decision or you
stability.
want to implement it. Yeah.
Right. Okay.
So there are papers on both sides. So if you
Yeah.
have come up with a simpler model, that's fine. Yeah.
Okay.
Yeah, that's fine.
So either one would work for this.
What worked for this? Yeah.
I was thinking to do something about the stability of decentralized controller, how that can be guaranteed.
There's no way to guarantee it. Oh, if you have the controller, you can check its stability.
Right. For
If you
single-
want to design the controller, there is no general theory for this. Again, it's heuristic.
Okay, so in what direction could I go with decentralized control?
There are a lot of papers you can read. Go to transactional smart grid and transactional power systems and transactional automatic control. Three different genres: automatic control, power system, and smart grid.
Automatic control
Yeah.
process.
A lot of papers on this. They come up with sufficient conditions for designing controllers. And there are a lot of ideas. They're good, but they're not as general as what you think.
Okay, so I could basically just start doing some sort of survey of what.
Survey
has
of a
been done.
lot of the recent. There are a lot of recent papers. So pick some of them, do a survey of those.
Okay.
Yeah, great.
Thank you.
Professor,
Sure.
I have also a question about the project. I got two questions. One about the project and the other one about the generator.
Okay.
Because I used to have like a house like near a lake.
Okay.
It was for my family. And we have like a 1.5 kilowatt generator
Okay.
because there's no grid in that place.
Okay. Sure.
So every time we turn on the washing machine, there was the example, the voltage goes down because you can see all the light bulbs.
Voltage goes down, right?
Yeah.
Of course, because there is some induction. Now, if you look at the generator is about mechanical power. Mechanical power is active power. But on the other hand, to generate active power, you have to talk about electromagnetic field. You have to go through coil.
Yeah.
Coil is what? Is reactance. Reactance is different. So if there's a capacitor bank, reactive power goes up. If there's reactance, reactive power goes down. So when you turn it on, your intent is to get active power, but active power goes through reactance, and reactor consumes the reactive power. Turning reactive power down tries to reduce voltage. And that's another thing that we talk about.
So it's like a loop.
It's a loop, yeah.
Okay.
Yeah. But it's not a lot compared to what you see on mechanical part.
Yeah, it's not a lot.
You see that some flickers probably.
Yeah, some figures go down,
Yeah.
like, and you see that it's fighting, the generator is fighting, trying to get
Sure,
up again,
yeah.
and
You know,
suddenly,
that's what part of what I mentioned, that you converge to the wrong equilibrium.
Yeah.
So that's the wrong
and
equilibrium.
it's fighting. You see it's struggling all the time. The generator. But the project I'm thinking about, I got a lot of ideas.
Sure. You're mechanical?
Yeah, I'm the mechanic.
How hard is this? Have you ever seen things like
I
this?
got a meeting right now about that, about calculating also the benchmark point, the 59%.
Oh, there's another course on this. Okay.
Yeah, there's a course about, and we got a lot of course about the energy. So,
Oh, okay.
But it's okay because we got the meeting now at 4 p.m. So it's going to be
Okay,
great.
good.
And the thing is, I used to work in a small hydro business,
Okay.
and the thing is that it's very popular to the small hydros, 2 megawatts until like I don't know, 10 megawatts, to put it in the distribution grid.
Okay.
So I would like to have like a project about distribution grid, but I don't know how to do it.
Okay.
But do you think it's going to be like, it's a good project? Or?
I didn't see the challenges. But if you want to do a project, you either want to pick existing papers or you want to do something new. If
Yeah.
you want to do something new, I don't see the challenges. So
Yeah, what I'm thinking about is like pick a project like from somewhere in where I know it's going to be the project, and like put the grid and try to do like the optimization about also how the cost and the prices that I'm going to get.
Yeah, I'm going to talk about probably the end of next lecture about DG, distributed generation.
Okay.
And that's about a small generator at the distribution level to optimize everything. Hydro is a special case of that. We talk about it, but after solar.
Okay.
So we do power, wind, then solar, then DG.
So it's going to be okay because the thing is
Yeah.
like to connect it to the grid and then like try to make like the power purchase agreement and everything.
Yeah.
Because to do like the financial part.
Sure. Yeah.
It's like a project because
No, you can do it. Yeah, of course. There are a lot of projects on demand response for DG.
but it's okay because it can be really interesting because then it's a real project that you can sell it to
Search,
the
yes,
company.
search. There are a lot of papers on transactions with smart grid.
Okay.
If you use the right keywords, you can find a lot of papers around this.
Okay.
That how we can have financial transactions at distribution levels for a small generator, not bulk power.
But for a project, you think it's better to analyze a paper or analyze a real project and try to estimate the flux? Because
You can do either way, either way works. You can get data, try to calculate something.
because I can sell that one.
Okay.
If I do it, I can sell it. It's like you can have this like these incomes for the next 20 years, and I can play with also with the fluctuation of the water.
Yeah, I'm telling you, there are a lot of projects. So if you know what utility companies are already doing,
Yeah.
it's so complex that you cannot easily get into the business.
Okay.
So because you just see the operation part, or you just see, for example, the market part, you don't see the whole thing. Like, for example, how can you guarantee that the utility company doesn't destabilize the network, satisfy all regulatory assumptions and conditions? So if you talk about the whole spectrum, that what are the liabilities and responsibility of a utility company? What are the actions that they're allowed to take? And what are the things that they try to hedge? And then you would say, okay, it's not as easy as you think. But there are a lot of papers around. The best thing is just read papers and see what are the challenges with DG. The first thing that you can imagine is the power goes in the wrong direction. If you generate power, a utility company doesn't understand that if the power is going in the wrong direction because you produce power, or there is the fault in the system. Because we consider the common way of detecting fault is just looking at the power, going that way or this way. So there are things, when you talk about the operation of a grid, it's very complicated than having some having an idea, say I implement that idea, but it should be connected to other things.
No, but the thing is that this project analyzing everything, like the reverse of the flux, the same as a project. It's like when you present a project to the centralized, they're going to say, okay, but give me the studies about the...
Yeah, just try, do your best, see what happens. Yeah, we're happy to read it, yeah, of course.
Okay. I will try.
Yeah, sure, great.
Okay, Carl.
Basically, what we say is that he knows that. I'm trying to understand what we use by sense. He knows that. Because what